Hello, and welcome. My name is Vlad, and we'll be doing this webinar. So this is the fifth webinar for COMPOS, year 10, and today's topic is DC circuits, so electricity, effectively. Now, there are a few questions here in the chat to begin with. What are the topics that we will cover in COMPOS? So let's have a look. I'll share my screen. If you go to our website, probably the easiest way to look at webinars, and you can say year 10 webinars, and here are the topics and the dates. So you can see which topic we are doing today. So today is the 27th of October, and we're doing DC circuits. So I've answered that one. Do we need a digital writer band to connect to PCs for the tutorials? Ideally, yes. We will talk about this tomorrow. Tomorrow is in intro webinar. I'm using a board like this. These start at about £20. Or you can even find cheaper ones. I think I bought one like this for £11. It was secondhand, of course. But yeah, and I use a pen to write. You don't have to have it, but it does help. We'll talk about it tomorrow again on the launch webinar. How do I resubmit the form tutorial? The forms, the tutorial, some of the times I put won't work for me anymore. Oh, please email us. Okay. Yeah, please email us. And please be patient because we have 1,000 students to sort into groups in just a matter of a few days. How will the launch webinars work? You just connect tomorrow and we will explain everything. Just use the link for tomorrow. Okay, I think I didn't get the link for the past webinar, so the recording is available. So the recordings, if you go onto our into website, you have the YouTube playlists, all COMPOS webinars. This is for all year groups. If you click on that, you will see all webinars for all years and all year groups. So there's lots and lots of them. Or you can specifically go to year 10 webinars. And the year 10 whiteboard is the whiteboard that we're using today to do. So I hope that answers your question. Everything is on our website. Okay, so let's get started. DC electricity. It's one of my favorite topics. I'll post the link here in the chat. Okay, so electricity. In simple terms, if you take a battery and a light bulb and connect it using wires, well, magic happens, right? The bulb lights up. So what's actually going on here? So there are charged particles, which are electrons in this case. They flow through the battery. They flow through the wires because wires have free electrons inside. They're pushed by the battery. So it's not that the battery is providing the electrons are already inside the wires. Look, if we stop the circuit, you can see that the electrons are still in the wire. What the battery does is provides some kind of pushing force that pushes these electrons through the lamp. We say that the battery provides energy to the electrons, and then the electrons use that energy to do useful work, in this case to light up the bulb. So you can say that the battery pushes the electrons and the electrons go through the light bulb. They do useful work converting that electrical energy into light. And there are some key characteristics. So electrons, as you can notice, the electrons flow anti-clockwise, but if we switch to current flows clockwise from plus to minus. So the yellow on the battery is plus, the black is minus. So this is the direction of the current. The reason why these are opposite, because when the first physicists were doing experiments with electricity, such as Franklin, for example, they didn't know about the existence of electrons. So they just assumed that electricity was a positively charged fluid. that flows from the battery through the wires? Because, well, you can't see electrons. You still can't see electrons. You can just deduce their presence. Anyways, there are characteristics such as the current. Current simply measures how many coulombs of charge. So how many coulombs of electrons, how many bags of electrons pass the wire in a second. So 0.9 amps means 0.9 coulombs of electrons per second. So let's make a note of that. Electrons, if you will, you can put electrons in a bag and call it a coulomb. 1 coulomb is a bag of electrons. It contains 625 electrons. Or simply 6.25 times 10 to the 18 electrons. Yeah, so that's my coulomb of charge. And a current of 0.9 amps simply means 0.9 coulombs per second. Right. Hope that makes sense. The other important characteristic is, of course, the voltage. And if you measure the voltage across the battery, is 9 volts. So the 9 volts means so the coulombs coming into the battery have less energy than the coulombs coming out of the battery. And the difference in that energy is 9 joules per coulomb. Every coulomb receives 9 joules of energy as it passes the battery. So you can think of it, the battery raises the energy of the electrons. They pushes the electrons to a higher energy, I don't want to say level, because it's not pushing them to high energy levels, it just pushes them to a higher potential. Cool. And you can think of it like this. So 9 volts means 9 joules per coulomb. 9 volts means 9 joules per coulomb. And 1 amp, or 0.9 amps, 0.9 amps means 0.9 coulombs per second, per 1 second. And that's important. And there are 2 formulae. Current is the charge divided by time. And voltage is the energy divided by charge. Energy per charge. Okay, that's the definition. Hope that makes sense. And now we move on. And you can think of electricity as a water circuit. So this is what we call a water circuit. So you can see there's a pump, and the pump pushes the water to a higher level. Just like the battery pushes electrons to a higher potential, to higher energy. So the battery raises the energy of the charge. It pushes charge to a higher level, to a higher potential. Now then, as the water runs along these gutters and then rushes through a narrow pipe or slant, whatever that is, let's say it does useful work. So you could put a wheel there. So this water pushes through that resistor, and as it does so, it loses energy. energy. It goes from high potential to low potential. Low potential. And then there's a switch, so a tap. A tap is a switch, effectively. And then the water goes back into the pump, and the pump once again raises the electrons. So the pump does to electrons something to electrons that the electrons then can do work. Like, well, actually, the battery pushes the electrons along the circuit. But that's not the mechanics of how it does that. That's not really important. The idea is that electrons go from a low potential to high potential. So now they have energy. They're not charged. Don't use the word charged, because they are always charged. The electrons are negatively charged. They're always negatively charged. But they have energy. They get a kick from that pump. And if you look at a parallel circuit, and this is, sorry, this is the same idea here. So you could say that electrons, well, let's say electrons go, let's say they move this way. Let's say charge, the positive charge. You can say that there's 0 volts, so low potential, and high potential. And this is 9 volts. And the voltage is 9, so that's potential difference. It doesn't have to be 0, 9. It might as well be, let's say, like 5 volts and 14 volts. We don't know. We don't know the potential because the voltmeter doesn't tell us. The voltmeter just gives us the potential difference. Right. So potential is like the height above the ground. Okay? Potential is similar to height. Is that how you spell height? Yes. Low potential, high potential. So the potential difference is 9 volts. The voltage is the potential difference. So electrons get energy in the battery. If they use up that energy, so they still have plus 14 volts. And here they have plus 5 volts. So they lose 9 volts as they go through the lamp. They use up that energy. They go back to the battery to get more, and this cycle repeats. Let's look at a parallel circuit. In a parallel circuit, you have a pump. It pumps the water to a high potential. Let's say it's, don't know, 12 meters above the ground, whatever that is. And this is low potential. And that's, let's say it is 3 meters above the ground. It doesn't matter what it exactly is. The potential difference is 9 meters in this case. And in the case of the battery is the voltage. The voltage is 9 volts. So you can say that the electrons here have 12 volts of potential, still 12. And as they go through the resistor, they drop potential, they lose energy, and it goes to 3 volts. 3 volts, and then goes back 3 volts. It might as well be 0, 9, we don't know, but the key is the difference. 12 volts. If you would just say 0. Okay. So we say that this is 9 volts, 0 volts, 0 volts, 9 volts, 9 volts, 0 volts. Yeah. And then obviously, if you have a parallel circuit, you must have the same potential difference. You have the voltage on the first lamp and the voltage on the second line must be the same. V1 and V2 will always be the same because you get the exact amount of energy you get in the battery, you lose in either light bulb. This is always true for a parallel circuit. In a parallel circuit. Because we're talking about energy, we're talking about height, right? There's no way if you return to the original position, there's no way you can go through a different height change. Right. Now let's look at a series circuit, and in a series circuit, once again you have the pump. You lose some of the energy going down, and then you lose more energy going down, and then you go back to the original position. So let's say this is, well, for simplicity, this is 0 meters, and this is 9 meters above the ground. And let's say point B is 6 meters above the ground. So as an analogy, you would have 9 volts of potential here. You would have 6 volts of potential here, and you would have 0 volts of potential here. And then you would say on the voltage on the resistor BC, voltage on the resistor BC is the potential difference is 3 volts, and the voltage on resistor AB is 6 volts. So they have a potential difference. Now, you can see that if you're thinking of the height, you'd see that it will always be true that the voltage on the pump is equal to the voltage on the first resistor plus the voltage on the second resistor. This will always be true. And the same also that the current, the amount of water going through the pump is exactly the same as the amount of water going through this. Current on the pump is equal to the current 1, and it's the same as current 2. That's important. And for the series circuit, you can see that the voltage, the difference V1 and V2, V1 has to be V2, and it's the same as the voltage on the pump. And the current, the amount of water going down here, the amount of water going down here, I1 plus I2 must equal to the current in the pump. The amount of water going through the pump is the sum of these two waters going down these two gutters. So that's the rules for circuits. So in a parallel circuit, V1 is equal to V2. Current 1 plus current 2 is equal to current on the battery. And the same here is equal to the battery. Now for the series circuit, the voltage on the battery is equal to V1 plus V2, and the current in the battery is equal to current 1 plus current 2. Lovely. If the electrons split up, isn't there less energy? No, there isn't. There's fewer electrons, but the energy per electron, the energy per electrons, the height difference, it has to be the same. Look, if the pump raises the water 9 meters above the ground, whichever route you take, you will drop 9 meters. Yes, sorry, I made a mistake here, of course. Current, yes, current in the battery is equal to current 2. Okay. I hope that makes sense. And look, next time you think of a circuit, you'll think of water. Now, if you have 2 resistors in series, imagine you have water and water needs to pass through 2 resistors. It's harder to pass through 2 resistors, through 2 narrow gutters. So resist is like a narrow gutter. So the total resistance is greater. And resistance, I remind you, resistance is the voltage divided by the current. Is the voltage you need to apply versus the current that you get. And for in a parallel circuit, in series, the total resistance is equal to R1 plus R2 plus etc. And in a parallel, the 1 over the total resistance is equal to 1 over R1 plus 1 over R2 plus etc. So this is a series connection. So you would have the total 18 plus 64, 82. So the total is 82 ohms. It's quite straightforward. Here you have 3 resistors in series, so that's 42 ohms, 105, 5 plus 16, 121 ohms, etc. I'm not going to do all of them. It's quite easy, right? So here it's kilo ohms. You just keep that in mind. This is kilo, and nothing. So 3,000 plus 10,000, 13,000 is 14,500 ohms. And here we have mega. So that's 100,000, 500,000, and 100,000. So 600,000, 700,000. So 0.7 mega ohm is the, I think so. Yeah, 0.7 mega ohm is the total resistance. Now, when you have resistors in parallel, then you have a different situation. So for example, for the first one, you have a 6 ohm resistor and a 12 ohm. So the zigzag is the old-fashioned way. So sorry, it's a picture from an old book. It's the old-fashioned resistor. So 6 and 12, 6 ohm and 12 ohm. So 1 over R total is 1 over R1 plus 1 over R2. So 1 of the total resistance is 1 over 6 plus 1 over 12. Simplify that, so multiply this by 2. So it's going to be 2 plus 1 over 12, which is 3 over 12, which is 1 over 4. So 1 over R is 1 over 4, so RT is 4 ohms. So this is 4 ohms. So what interesting, the total resistance is lower. Also, the total resistance is lower than the lowest resistor. That's also important. Now, in the second one, you could use the formula, but you could use a nice trick. Look, you have 24 and 24. If you have 2 identical resistors in parallel, the total resistance is halved. So 24 and 24 in total make 12 ohms. And now you have 12 and 12 in parallel. So 12 and 12 in parallel, that's overall 6 ohms. Let's check that it actually works. So this is question 1. Question 2, 1 over 12 plus 1 over 24 plus 1 over 24. And you'll need to do 1 over that, right? So resistance is that. So it's 1 over, so that's 2. 2 plus 1 is 4. 4 over 24, which is 1 over 6, which is 6 ohms. So it works. So number 3 is 30 and 60. Now, here you can use the same trick. You can say a 30 can be drawn as 2 60s. So you can do 60 and 60. 60 and 60 make 30, right? In parallel. So you can see 3 60s. 3 60s in parallel, that makes 20 ohm. You could use the same trick in this one, but I wouldn't bother for question 4. So for question 4, you could say 1 over 45 plus 1 over 15. Multiply this by 3. You get 4 over 45. So resistance is 45 over 4, which is 11.25 ohms. 11.25 ohms. Okay, I really hope you're getting this. The formula is quite straightforward. Don't forget to do 1 over R when you do it. Number 8 is 4 resistors, 4 identical resistors, so it's just divide by 4, so that's 5 ohms. Number 6 is 2 identical resistors, so it's 250 ohms. Anything interesting? That's about it. Now we have a combinations of series and parallel. So here you have 200 combinations. So first you do the combination. 300 and 600. So 1 over 300 plus 1 over 600. That's going to be 3 over 600, which is 1 over 200. So that's a 200 ohm resistor. So you can replace that with a single 200 ohm resistor, and then the total is 453. So it's bam, bam, bam. Okay. Number 2, so you have this parallel combination. So you start with the parallel combination, 1 over 200 plus 1 over 500 plus 1 over 1,000. So multiply this by 5, multiply this by 2. So that's going to be 8 over 1,000. So resistance is 1,000 divided by 8, which is 125 ohms. So in total, this thing is 125. So you add them up, so that's 700, 1,000, 1,125 ohms. That's the total resistance. So in question 3, you have 16 and 12. So first you do this combination, so that will be 28 ohms and 14. So you can think of it's 3 28ths, so 28th over 3, 28 over 3. So that's 9.3 ohms altogether. 9.3 plus 16, and that's 15.3 ohms. Right. In number 4, you would calculate this combination first, then this combination first, and then you just add them up because they are in parallel. Okay. I hope that makes sense. Now, this question, this is from the assignment, but I'm going to modify it. I'm going to say, let's say this is 2R, 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 and this is 5R, 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 and 5R. So this is an infinite chain of resistors. Apologies. So there's a question about the difference between these webinars. So please join tomorrow and we'll explain in detail what we're doing. In short, you have tutorials in small groups where you will be constantly talking to your tutor. And this webinar is for, well, we have 80 people joining at the moment. And this is just me talking and answering your questions as they come in. So it's different format. You would have 8 students per, and you will be with a university student as your tutor. Okay, so we have an infinite chain of resistors, and we need to find the resistance between A and B. Find the total. Find the total resistance between A and B. Well, think of it that way. Imagine we found that resistance. And the idea of finding the total resistance is that you can replace the whole thing with a single resistor. So imagine you could replace that with a single resistor between A and B, and we call it RT, R total. Nice. That's what we want to find. We want to find the total resistance of the combination, and we are able to replace it with a single resistor. Now, if we were to add another chain on the left, adding another chain on the left doesn't change the total resistance. Adding another link on the left, you would have the total resistance that you're looking for, and then you're adding a 5R here and a 2R here. And let's call it, this is point A and point B. Let's call it point C and point D. Well, because there are infinite chains, adding another link doesn't change anything. So the resistance across AB is equal to resistance across CD. And that's what we're going to explore. So from here, we have this combination. So 2R, 5R, RT, and yeah, that's what we're looking for. So to find the total resistance, you're going to find the total resistance of this. And you can use any formula for parallel resistors. I haven't said that before, but for parallel resistors, for two parallel resistors, total is R1, R2 divided by R1 plus R2. That's a useful formula to remember. It's just a rearrangement of this formula. And so we have this combination. It's called R3. Let's call it R3. And it's RT multiplied by 5R divided by RT plus 5R. And then plus this, so the total. So resistance across CD is equal to 2R plus RT times 5R divided by RT plus 5R. And we know that this resistance across CD is resistance across RAB, which is RT. And all we need now is to open the bracket, to solve this equation. Solving this equation, so multiply both sides by RT plus 5R. So 2R multiplied by RT plus 5R plus RT times 5R equals RT bracket RT plus 5R. Okay, 2R RT plus 10R squared plus 5R RT equals RT squared plus 5R RT. Oh, nice. This cancels. We get RT squared minus 2R RT minus 10R squared equals 0. And this is a quadratic equation. If you divide by both sides by R squared, you get RT over R. squared minus 2 RT over R minus 10 or 0. Let RT over R equal X. So X squared minus 2X minus 10 equals 0. 1 negative. What am I doing? It's X squared minus 2X plus 1 equals 11. X minus 1 squared equals 11. X equals 1 plus or minus root 11. And of course, it's the positive 1. So RT over R is 1 plus root 11. So answer, the total resistance is 1 plus root 11 times R. That's it. That's how you do it. I don't think I could be even more specific for this particular question. It is a difficult question, and I think it's labeled with a star. But yeah. Let's have a look at a much easier task. And this task builds your intuition with circuits. It's called voltmeters by proportion. Find the readings on each of the voltmeters in the circuits below. And these are tasks from an old O-level book. And these are really designed to just for, well, these are really designed to practice for practice. Okay. Now, you can see there's a battery. There's a 12-volt battery here. And there's two identical resistors, a 100 ohm and a 100 ohm. So the voltage, what would the voltages be? Or if you remember what we talked about water, you get energy, you lose some of the energy in the first resistor, you lose some of the energy in the second resistor. If they are the same resistance, it makes sense to assume that you lose the same energy. So that's going to be 6 volts and 6 volts. Very simple. So if you see a circuit like that, you automatically know that this is 6 volts and 6 volts, and we can test that. Let's do a battery, a resistor, and a resistor, and some wires, and okay, we have a voltmeter, so let's this be 12, and this resistance is 100. And you can see that this is 12 volts, this is 6 volts, and this is 6 volts. And interestingly, if you measure the voltage across the wire, it's 0 volts because you don't lose any energy in the wire. That should make sense. You only lose energy on the resistor, and this voltage is the difference in energy before and after. Okay, so the 24 volts, so there's a 5 and a 10. Well, it makes sense that it's 24, so it's split in proportion to 5 and 10. So you split 24 in proportion 2 to 1, and that is 8 volts and 16 volts. Right. Working out for these questions? Well, it's a potential divider, as a matter of fact. You could say that the voltage V1 divided by V2 is R1 over R2. And then you know that V1 plus V2 is 24. And you can solve these simultaneously, but that's an overkill. You don't need to solve them simultaneously. You just see the answer. Just to be 8 and 6, because that's how they are split in proportion. That's what I'm talking about. We are developing an intuition about circuits. Let's look at the next one. You have 24 volts, and it splits in proportion of 7 to 3 to 2. Well, then it makes perfect sense. Say this is 14 volts, this is 6 volts, and this is 4 volts. They have to add up to 24, and they have to be proportional to 7, 3, 3, and 2. So it's 14 to 6 to 4 is the same proportion as 7 to 3 to 2. Here, we have two resistors, and we know that this is a 6 and this is an 18. So this is 3 times more resistance. So this is 9 volts. So this must be 3 volts here. If you would place a voltmeter here, it would be 3 volts. And then if this is a 3 and a 9, that this is 12 volts. Now, this is slightly trickier because you have a 6 and a 6, but you know already you know that in total, that this can be replaced with a single resistor, which is 3 ohms. A 6 and a 6 make 3 when they're in parallel. So you have 2 and 3, and it's 10 volts split in proportion of 2 to 3. So this must be 4 volts, and this must be 6 volts. Okay. Now this, you have 20 and 30. You find the total resistance of these. So I'm guessing that would be 12 volts. So 20 times 30. So the formula is R1 times R2 divided by R1 plus R2. The total. So our total is 20 plus 30. So it's 600 divided by 50, which is 12 ohms. This is 12 ohms. So this is 12 and 6. So the proportion is 2 to 1. So that's 8 volts. And this is 4 volts. So the answer is 8 volts. Hope that makes sense. Yeah, you just do a proportion. The ratio of voltages is equal to the ratio of resistors. That's for but only for series circuits. It's called the potential divider equation. Potential divider equation. But once again, I'm not trying to show you rigorous proof of these. I'm trying to show you how you intuitively should see a circuit. And when you're trying to solve a circuit, you need to use your intuition. Otherwise, you'll just get lost in calculations. You kind of need to see what's going on, try to imagine what's going on, and yeah. Now, ammeter by proportion works slightly less intuitively than voltages. Let's see. Well, here it's quite easy. You can say, well, there's a battery here, so the current starts from here, so current flows. It's like water. How much water will flow through the circuit? If you know that 3 amps flows here, 3 amps, but there's no other way for the electrons to go. They have to flow through the battery and then through that ammeter. So this is also 3 amps. So in a series circuit, the current is always the same. And it's 3 amps here. So this is a super easy question. The current is the same everywhere. Now here, you can see that the current flows that way, that way, that way, that way, that way. So this is 4 amps. So still 4 amps, still 4 amps, still 4 amps, still 4 amps, still 4 amps. So in this ammeter is going to be 4 amps. Now, something interesting happens here. At a junction, the current splits. Some of it goes here, and some of it goes here. But look, the resistors are identical, so the current is equally likely to go one way or another. Therefore, you have 2 amps here and 2 amps here. Once the 2 amp currents join up, they become 4 amps and the cycle repeats. Current is like water. Water doesn't go anywhere else. It just keeps on flowing. Or you can think of cars on a road. If you have 2 cars on this road, 2 cars on this road, they will eventually end up on this road. So this road will register 4 cars. Now we get to the less intuitive part. We have 3 amps here. So 3 amps. It's either too thin or too thick. So 3 amps. 3 amps. So it's still 3 amps in this ammeter. Now 3 amps flows here, and now the 3 amps splits. Some of it goes up, some of it goes down. Now we compare the resistors. This is a 4 ohm and a 2 ohm. It is harder to go through the 4 ohm. It's easier to go through the 2 ohm resistor, therefore more current will flow down. So 2 amps will flow this way and 1 amp will flow that way. So we have 2 amps in this ammeter and 1 amp in this ammeter. And let's confirm that. So how can we do that? We'll restart. There's a 6, a 4, and a 2. So it's a 6. A 4. And a 2. A 6, a 4, and a 2. We'll adjust the voltage until the current is 3 amps. Okay. So we have 3 amps in this wire. 3 amps, 3 amps, 3 amps, 3 amps. And then we see that here we have 1 amp going through the 4 ohm resistor. There's 1 amp, and there's 2 amps going through the bottom resistor. So it makes perfect sense. Take a snapshot of this to show that this is in fact true. This one, now, this looks like a complicated circuit. Actually isn't. So there's a battery here. There's some current leaving the battery. Oh, it's actually 10 amps. 10 amps leaving the battery. And now if you look at these 4 possible pathways, so there are 4 possible pathways for current flow. So and each of them is equally likely because the resistors are all the same. Therefore, you would have 2.5 amps in each ammeter. 2.5, 2.5. Now, here you have 2.5, 2.5. They join together to make 5 amps, 5 amperes. And then you have a 2.5 plus a 5, which makes 7.5 amps in this ammeter. Okay, and here we have a battery. We have a current flowing. The current splits, rejoins, and flows back into the battery. So this is 1 amp here, and this is 8 ohms. This is 4 ohms, so this must be 2 amps here. So 1 and 2, that must be 3 amps. So this would be 3 amps here, 2 amps going that way, 1 amp going this way, still 3 amps. This is how current works. And lastly, we have a battery and the cell technically, but don't worry about it. This is 3 amps. So a 10 ohm resistor with 3 amps of current flowing through it. Then 15 would have proportionally less, so you would divide by 1.5, so that's 2 amps of current. It's just proportional to that, inversely proportional. 2 and 3, that's 5 amps. Then 5 amps splits into proportion of 20 to 30. 20 to 30. That would make 3 amps going here and 2 amps going here. Hope that makes sense. Apologies, I can't keep answering the questions. There's a few questions coming in. I'll try to answer them later on. Okay. So there's a few questions here. Study the circuit. Find the total resistance of the circuit. Find the readings on the ammeters. Well, basically these are all solve the circuit. So solve the circuit means to find all the currents and all the voltages. So solve the circuit. So here you have current flowing here, then current going that way, current going that way, and yeah, so you need the voltages and the currents. Okay, let's call this a V1. Let's call it V2, V3, and V4. The voltages on the corresponding resistors. Solve the circuit. Okay, so and this is current I1, of course I1. This is I2, and this is current I3. Now we can start by finding the total resistance of the circuit. That's a good idea. So the 4 and 4, that's 8. 8 and 8 in parallel, that's a total of 4. 4 and 6, 4 and 2, that's 6. So the total resistance is 6 ohms. So the total current is the voltage is 12 volts divided by 6 ohms. That's 2 amps. So there's 2 amps. 2 amps. So I1 is 2 amps. The current through the battery is 2 amps. Now, this is 2 amps. Now we can see that some of the current goes up, some of the current goes down, but this is 4 and 4, that's 8, and that's 8. So we can immediately say that this is 1 amp, this is 1 amp. So I2 and I3 are both 1 amp. And then for voltages, well, we can use the Ohm's law. Ohm's law, that voltage is current times resistance. So V1 is current 1 times resistance 1. So that's 2 amps multiplied by 2 ohms. So that's 4 volts. V2 is current 2 times resistance 2. So that's 1 amp multiplied by 8 ohms, which is 8 volts. V3 is I3 times R3, which is 1 amp multiplied by 4 ohms, so 4 volts, and V4 is the same, 1 amp times 4 ohms, which is 4 volts. We've solved the circuit. We've solved the circuit by finding all the all the voltages and all the currents. Is the resistance multiplied by A1 equal to the other resistance by A2? I'm not sure what that refers to. Is the resistance... Oh, yes. Yes, that's you got it. Number 2. Okay, so we don't really need to worry about what's written here. Just need to solve the circuit, right? So solve the circuit, though, you start by drawing currents and labeling them. So we know that this is 1.33 amps. So we can already label that this is 1.33 amps. Some of it goes up, some of it goes down. So this is 8 ohms, and this is 24. This is 24 ohms altogether. And so there's 3 times more current going up than down. So you would split 1.33 divided by 4, which would be 0.33 amps. So this is 0.33 amps. And this is 1 amp going up, 1 amp going up, 0.33 going down. Okay, so good. So we know the currents. And now let's label these V1, V2, V3, V4, the voltages on each resistor. So V1 is the current times the voltage. So 1.33 times 3. So that would be 4 volts approximately, 3.99, but 4. V2 is 1 amp times 8, so 8 times 1 is 8 volts. V3, that's 0.33 times 12, which is 4 volts, and V4 is also going to be 4 volts because it's the same current and the same resistance. So, okay. And the currents we already know. And 5, find V1 and V2, find the currents. We know that this is 1 amp. Well, if this is 1 amp, then this is 6 volts and 6 volts. So it must be 6 volts and 6 ohms. So they have to be the same. So this must be 1 amp. And this is 1 amp. So this must be 2 amps here. 2 amps, 2 amps, 2 amps, 2 amps. Now, V1 must be current times voltage. So V1, I1 times R1 must be 1 times 6, 1 times 6, which is 6 volts. So this is 6 volts. This is also 6 volts, of course. Now, V2 is I2. Interesting. We don't know. Okay, so V2, because this is 16 volts and this is 6 volts. So imagine if you're trying to find the you're trying to go around the circuit. So you get 16, so your potential here is plus 16 volts. You lose some of that energy here, and then you lose some of the energy here. So here you end up with 0 volts. And you know that it's 6 volts here, so this must be 6 volts. So the potential difference here is 10 volts. So V2 is the voltage of the battery minus V1. which is 10 volts. If you think about it, you get 16 volts in the battery. You lose 10 here, you lose 6 there, you go back to the battery to get some more. In whichever way you go, you lose 6 this way or this way. Hope that makes sense. We can actually, can we do this? I think we can. Let's say this is six and six, so that's 3, and that's 6, and that's 10. 3 and 6, 20, I'm guessing. So this must be 20 ohms. This must be 6. No, that doesn't make sense. 10. Okay, that makes sense. So you can see that this is 10 volts. This is 16 volts. So each of these must be 6. This is 6, and this is 6. Right? So they must be the same. Not because they have the same resistance. They would have the same voltage even if they have completely different resistance. Look, I make it 159, one is 6. This is 8.34, and this is 8.34. They both have the same voltage, even though they have completely different resistance. So, okay. So overall, this is Kirchhoff's second law, in fact. And this is 10 volts, and V2 is 10 volts. So resistance, R2, is the voltage 2 divided by current 2, which is 10 volts divided by the 2 amps, which is 5 ohms. And that's, as a matter of fact, what we did here. This was 5 ohms. Find the total resistance of the circuit. Well, 6 and 6 make 3, so it's 5 ohms plus 6 times 6 divided by 6 plus 6, which is 5 plus 36 over 12, 3, which is 8 ohms, is the total resistance of the circuit. Okay, and number 7. When S is closed, S is the switch, the ammeter reads 3 amps. When S is open, the reading is 2 amps. What are the values of R1 and R2? So when S is closed, that means the current will not flow through the resistor 2. So S closed. R2 is not involved. So the circuit becomes just R1 and 6 volts. And we know that the ammeter is reading 3 amps. So R1 must equal to the voltage divided by the current, which is 6 divided by 3, which is 2, ohms. S open, when S is open, then you have two resistors in series. So this is still 6 volts. This is 2 amps. This is R1, which we already know that this is 2 ohms. This is R2. Okay. But we know that the total resistance is voltage divided by current, which is 6 divided by 2. That's 3 ohms. So R2 must equal to 1 ohm. That's a nice question. And use Ohm's law to find the readings on the voltmeters V1, V2, V3, and V4. Now, let's have a look. What do we have here? So we have 20 volts here. And okay, so we need to find voltages. Cool. We just need to solve this circuit effectively. So, I mean, they can ask anything. They can ask whatever they want. We need to solve this circuit. We need to find all the voltages and all the currents. Let's start by finding the total resistance. The total resistance. Well, we can see a combination of 20 and 20, and that's a total of 10 ohm. 10, 15, and 25. So the total resistance is 10 plus 15 plus 25, 40, 50 ohms. So the current, total current, is the voltage of the battery divided by the total resistance, which is 20 divided by 50, which is 0.4 amps. So the current here is 0.4 amps, 0.4 amps, 0.4 amps. Current doesn't flow through the voltmeters. That's one thing you should understand. 0.2 amps here, and 0.2 amps here because the resistors are identical. Then we go back to 0.4 amps, still 0.4. Okay, 0.4 everywhere. So current 1 is 0.4 amps. Current 2 is also 0.4 amps because there's no other way for current to flow. Yeah, that's fine. V1. V1 is the current times resistance, and current is 0.2 multiplied by 20, which is 4 amps. V2, well, V2 is a matter of fact, it doesn't make any difference because along a wire, the potential is the same. The potential doesn't change along this wire, and the potential doesn't change along this wire. So no matter how you connect the voltmeter to, you can connect it here, here, or here. The voltage is not going to be the same. 4 volts. 4 volts. V3 is once again current times voltage. Current 3 times voltage 3. So that would be 0.4 amps, current times resistance, of course, times 15. And that's 15 ohms, and that's 6 volts. So that's 6 volts. And V4 is current, so 0.4 amps multiplied by 25 ohms, and this is 10 volts. Let's see if that makes sense. This is 20 volts. This is 10 volts. This is 6 volts, and this is 4 volts. And this is 4 volts. Makes perfect sense. Because if you go around the circuit, so Kirchhoff's second law says if you go around the circuit, the sum of the voltages will equal to the voltage on the battery. So Kirchhoff's second law says going around the circuit, the circuit, the sum of voltages is equal to the voltage on the battery. So what does that mean? That means if I take a route, so I start from the battery, I go bam, 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 bam. If I take this route around the circuit, if I just walk around, literally walk around the circuit, I have 4 plus 6 plus 10, 4 plus 6 plus 10 volts must equal to 20 volts, and it is. If you take a different route, so if I take, for example, this route, if I go around this way, it's still valid, right? So it's 4 plus 6 plus 10 is 20. That's how Kirchhoff's second law works. And one last thing I want to do is solve this circuit. Now, this is a much more difficult circuit because, oh, actually it isn't. It actually isn't a more difficult circuit, but yeah. I'm going to do it in using Kirchhoff's laws. Sorry, I'm a bit rushed with Kirchhoff's laws here, but let's do it this way. Let's label the currents. Let's label this as current I1. This is current I2, and this is current I3. And Kirchhoff's first law, says that the currents at a junction sum to 0. The total current at a junction is 0. What that actually means is that means that I3 plus I2 must equal to I1. That's all it says. That's all it means. Sum of currents at a junction the sum of the currents is 0. Kirchhoff's second law says that Kirchhoff's second law says that the total voltage around any loop is equal to the voltage on the battery. The sum of the voltages is equal to the voltage on the battery in a slightly simplified manner. So let's label the voltages. Let's call it this V1, V2, V3, and V4. So we can say that V1 plus V2 must equal to 12. And here we have V3 plus V4 also must equal to 12. Nice. Well, as you can see, we have 3 equations. We have 7 unknowns. Not very useful. So we need some more equations. Well, we can say that V1 is 55 times I2. V2 is 5 times I2 because current is voltage, temperature, resistance. Ooh, that's nice. So we've eliminated two unknowns, V1 and V2. V3 is I3 multiplied by 30. V4 is 90 multiplied by I3. Good. And finally, yes. Okay, so let's rewrite these equations. V1 plus V2, so 55I2 plus 5I2 is equal to 12. And 30I3 plus 90I3 is 12. Ah, lovely. We can immediately find I2, which is 12 divided by 60, which is 0.2 amps, and I3 is 0.1 amp. Oh, lovely. And I1 is I2 plus I3, we already know, is 0.3 amps. So we can use Kirchhoff's laws to solve the circuit, and we can say that this is 0.3 amps. This is 0.2 amps. This is 0.1 amps. Okay, and the voltages, this is V1, is 55 times 0.3. Oh, sorry, 0.55 by 0.2. That's 55. That's 55 times 0.2. Oh, 11 volts. This is 1 volt. Oh, yes, of course. This is 30 times 0.03 volts. This is 9 volts. Now, let's use this to check Kirchhoff's laws. Check Kirchhoff's laws. So Kirchhoff's first law says that the sum of currents at a junction is 0. Well, we have 0.2 amps going in, 0.1 going in, and 0.3 going out. So 0.1 plus 0.2 amps, 0.1 amps plus 0.2 amps minus 0.3 amps is 0. That's true. Works. Kirchhoff's second law says that around any loop, the sum of voltages is equal to the voltage in the battery, or in other words, the sum of voltages is 0. So here, so if we go around this loop, in this direction, we gain 12 in the battery. So plus 12 we gain in the battery. We lose 11 in the lamp, and we lose another 1 in the lamp, and the total is 0. If we go around this way, if we go around this circuit this way, we gain 12 in the battery. We lose 3 in the first resistor. We lose 9 in the second resistor, and the total is 0. And finally, if we take this route around the circuit, which doesn't even involve a battery, Kirchhoff's second law works even with no batteries. Now, we lose 3, so minus 3 volts. We lose 9, but now we're going against the current. So the current is flowing that way. We're going against the current, so we're going uphill. We're going to a high, from low potential to high potential. So plus 1 volt. So apologies. This is high level stuff. If you don't understand, don't worry about it. 11 volts, and that's a total of 0. I've done several more webinars on this topic. I hope that makes sense, and it's explained in the assignment as well. So I hope that makes sense somewhat, and hope that was useful. Let's see if they have any questions. Right. Will this specific webinar uploaded to the COMPOS YouTube channel? Yes. Will the Miro board be available? Yes, it will stay unchanged. done, with the switch closed. Why the current would not go through R2? Because the resistance of R2 is 0. So if you imagine, if you replace this with a switch, and look, if I close the switch, current does not flow through the resistor because it's easier to flow through this switch. If I open the switch, it has to flow through the resistor because there's no other way to go. So here the current chooses the path, and it chooses the path of least resistance. Tomorrow is the same time as today. Yes, it's a different webinar. It's going to be in the year 11 webinar, so unrelated to you. But please join for the for the first part of the webinar tomorrow. So for about 40 minutes, we'll explain to you how COMPOS works, and then I'll say everyone who is in year 10 can go, and I'm going to do a year 11 webinar. Do we attend the webinar on both Tuesday and Wednesday? No, just one, just the Tuesday one, please. We can solve the net resistance. Yes, usually it's easier to solve the net resistance if you can. Okay. Can you please send the link? Okay, I have done that. If the electrons are split up, the parent, I've answered that question. Question 3 on that worksheet. Question 3 on that worksheet. I'm sorry, I'm not sure what's that referring to. Oh, that's a very good question. You open a switch in a parallel circuit, the electrons flow. The electrons are already inside the wires. They're not, the battery is not supplying electrons. Battery is just giving them a kick. So when you open the switch, the electrons just stay where they are. They stop moving. And yeah, they stay in the metal. The webinar ends at 7:30 London time. We have already finished pretty much. Did you host any webinars after 29/09? No, we had a break for a month. So no. We tend to use current. We tend to use current going from positive to negative, not electrons moving from. It's not electrons moving from negative to positive. Okay. Right. Tuesday, join on Tuesday, please, because Tuesday is year for. I mean, if you can't join on Tuesday, join on Wednesday. But Tuesday is focused on year 10 and 11, and Wednesday is focused on year 12 and 13. Sorry, I'm a bit overwhelmed with questions, and I'm really not feeling well. I'm a bit sick, so Is there a physical or non-mathematical reason why the total resistance is parallel to the resistance of the smallest resistor? Yes. Imagine you have a narrow door. Like resistance is how difficult it is to get through that door. If you add another door, doesn't matter what the door is, you now have two doors. It's easier to go through, right? So if you take the smallest resistor and add another one, it's always going to be easier than just one. So I like that convention that imagine you have a door opening to a building and you add another door. It's going to be easier for people to get into that building, no matter how wide the second door is. All right. Apologies. I have to stop. I know there's quite a few questions here, but I think I've answered all of them. In a parallel circuit, the current splits between them based on how much resistance. How do the electrons know? Well, it's a good question. They don't know. Of course, they don't. Um, if you take a bucket, if you take a bottle of water, and you make two holes in the bottom, one big hole and one small hole, you would have more water flowing through the big hole and less water through the small hole. How does the water know which way to go? Well, it doesn't, does it? It's being pushed by gravity, and it's more likely to go through the big hole. So the electrons are being pushed by the electric field, and they're more likely to go through the wide resistor, through the less resistive. I hope that answers your question. Okay, I'll see you all in 2 weeks' time. Well, I'll see you all tomorrow, and then I'll see you all in 2 weeks' time. All right, see you tomorrow.